Welcome back to Differential Equations. In this video, I want to talk about Fourier analysis. Fourier analysis is the process of taking a general function and rewriting it using a Fourier series, either looking for the infinite series to give you an exact way of representing the function, or just finding the first several terms in order to use a Fourier approximation of the function. In various contexts, one or the other might be more useful. In order for Fourier analysis to work, there's a couple of things that need to be true of the function. The first thing is that we can only do Fourier analysis on a function that is defined for negative L less than x less than L. And the second thing is that the function has to be periodic, and the period of the function has to be 2L. So this window from negative L less than x less than L is one full period of the function. One of the interesting things about functions is if you have a function with a period of t, it also has a period of 2t and 3t and 4t. So if it happens that the function between negative L and L repeats itself one or more times, it might still have a period of 2L as well as a larger period, and that will be perfectly fine. You can do Fourier analysis in that case. It's when you don't have these things that you start to have to answer some questions. And they're not difficult questions. So for example, let's consider the function f of x equals 1, or 0 is less than x is less than L. That's about as simple of a function as I can come up with, and still interesting enough to do something with here. Well, if that's the function we have, the immediate thing you should recognize is that this is not defined on that symmetric interval from negative L to L. It's just defined from 0 to L. And so we have to make a choice. We can choose the even extension, which says that f of the opposite of x is equal to f of x, or we can choose the odd extension, which says that f of the opposite of x is equal to the opposite of f of x. Do we have to choose one of these two things? No, absolutely not. Fourier analysis will work when you do not have an even or an odd function, you have something else. But if you do have an even or an odd function, then it really saves you a lot of time and effort. Because cosine is an even function and sine is an odd function. So if you have a function that you're trying to represent as a Fourier series and it's an even function, all of its terms will be cosine and none of its terms will be sine. Likewise, if you have a Fourier series that's an odd function, all of its terms will be sine, none of them will be cosine. That's a very simple way of reducing a lot of the work that can come into solving one of these problems. Which choice makes the most sense? Well, a lot of that depends on what the particular application you're looking for is. I'm looking at this in a bare bones mathematics sense, so I don't have a lot to go on. But I still have something. And so when I think about this, well, there's two things I can do. The even extension in this case, if I've got from 0 to L, this thing is 1. And then from minus L to 0, I take the even extension. It would be 1 there as well. And then it would be periodic. So it would repeat that again and again And again, that is a very boring function. It's just the constant function 1. And while we can look at that function, it's not going to be challenging because in the cosine series, the first term is a constant term. So you just have that constant term equal to 1, and you have the function represented. Now, if I try the odd extension, that gives me something a little bit more interesting. From 0 to L, the value of this function is 1. So from negative L to 0, the odd extension says it would be negative 1. And then this pattern would repeat. So it would go back to negative 1, and then back to positive 1, and back to negative 1, and back to positive 1. That's something that is interesting. And completely unrelated to the fact that I'm solving this problem, this is something that is interesting in application. Bouncing between two discrete states like this is the way that computer signals work. What we have here is the clock signal for a computer. I mean, sure, in a computer, generally we have this shifted up so that the low level is at 0. The high level might be at 1 or 2 or 5. But that's immaterial, right? Again, this is math class. We don't care about those kinds of applications. We just care about, can we do something with it? So let's do something with it. First, I need to figure out a way to write out this odd extension. I can't just say it's the odd extension of f of x equals 1, but maybe I can put something a little bit more clear into this. Well, between 0 and L, I got out the value of 1. And for the sake of being able to do some calculations, let's pick a value of L. How about 2? And then we get negative 1 for the mirror of that, which would be negative 2 less than x less than 0. We know that this is an odd function. We designed it to be an odd function. So that makes our lives a lot easier. If we look at the an terms, 1/2 integral from negative L to L, it'll be negative 2 to 2 in this case, of our function times the cosine of n pi x over L. L again being 2 in this case. F of x is an odd function. Cosine is an even function. If you multiply an odd function times an even function, you get an odd function. And when you integrate an odd function over symmetric limits of integration like this, you get 0 every single time. We don't have to actually do the calculations. We can use logic to reason that out. Now, if we look at the Bn sequence, this is the one that involves sines. F of x is an odd function, sine is an odd function. If you multiply two odd functions together, you get an even function. And even functions do have values going from limits like negative 2 to 2. And in fact, when you have even functions, you can make your life a little bit easier by saying that, well, this is just double what you would get if you just went from 0 to 2. That double will cancel out with the 1/2 that was in front before, leaving us with just the integral by itself now. And really brilliantly from that is we don't even have to worry about what our original function was. We have to worry about what our original function was. We don't have to worry about what our extension was. Because between 0 and 2, we have that original function. F of x equals 1 for 0 less than x less than 2 was what was defined for us. And then we said we were going to take the odd extension of that. We wrote down what it was so we could play around with the graph. But we don't actually need it in our calculations because we're only going to be looking between 0 and 2. And between 0 and 2, f of x is equal to 1. Like I said, this is about the simplest function that I could possibly come up with. All right, so what happens? Integrating sine is fairly straightforward. We're going to end up with 2 over n pi multiplied by, well, the inverse, or the integral of sine is the negative of cosine. And if you try to evaluate that, plug in 2 here. The 2's will cancel each other out. Plug in 0 and everything cancels out. Cosine of 0 is not 0. I'm trying to write and talk at the same time. Cosine of 0 is 1. Cosine of n pi is sometimes 1 and sometimes negative 1. Right? When n is 1, cosine of pi is 1, and then we take the negative out here and we get negative 1. When n is 2, cosine of 2 pi is positive 1. I think I said that backwards already. I'm sorry. Cosine of n pi, when n is 1, we get negative 1. Then we have a negative in front that gives us a positive 1. When n is 2, cosine of 2 pi is positive 1. Take that negative in front, and we get negative 1. Cosine 3 pi would be negative 1. Take the negative in front, that gives us a positive 1. And so on and so on. So when we have an odd value of n, then we're going to end up with 2 over n pi times 1 plus 1, or just 4 over n pi. When n is even, we're going to end up with 2 over n pi times negative 1 plus 1, which is, once again, 0. Right? So I get just odd values of n. A trick that you might remember from a previous course is that we can write n as 2k minus 1. When you plug in k equals 1, you get 2 minus 1, which is 1, so you get n equals 1 as your first term. When you plug in k equals 2, you get 4 minus 1, which is 3. K equals 3 gives you 5, k equals 4 gives you 7, and so on and so on and so on. Depending on if you want to start at n equals, or k equals 1 or k equals 0, and whether you want to start at n equals 1 or n equals 3 or somewhere else, that changes whether you have that plus or minus. There's a lot of ways to go about it. There's no one right one. This is just the one I happen to choose here. All right, so we'll plug that in. Our function is the sum. It would be n goes from 1 to infinity of an times the sine of n pi x over L. But we figured out that if we write n as 2k minus 1, we can take the sum k goes from 1 to infinity, ak, which is 4 over 2k minus 1 times pi, times the sine of 2k minus 1 times pi times x over 2. If you don't want to deal with the summation, you can just plug in those first couple of numbers and figure it out. So you have, right, k equals 1, you'll have 4 over pi times the sine of pi x over 2. Plug in k equals 2, you'll have 4 over 3 pi times the sine of 3 pi x over 2. 4 over 5 pi times the sine of 5 pi x over 2, and I'm running out of screen over here, so I'll stop at that. All right. But since I was able to fairly easily find this closed form in this particular case, that gives me one other place that I can start playing around with that. Let me jump over to Desmos, and you can see on my screen here, no, that is the larger one. Okay, I thought I could get a little bit larger than that, but I cannot. That's okay. But you can see if you look over here on the left-hand side that I've set up my function. From -2 to 0, it's -1. From 0 to 2, it's +1. And then I put in one more cycle just to get a little bit more there. And then I've put in my summation with a stopping point of capital N that I have on this control arm. Let's shrink that down so we can actually see the graph a little bit more. And let's turn on that graph. When n equals 1, again, that's k equals 1, but Desmos doesn't let me change the index away from little n, so we'll go with it, it's fine. When k equals 1, we just have that first term, 4 over pi times the sine of pi x over 2. And there is your graph. 4 over pi is a little bit larger than 1, so the peak of this graph comes out a little bit larger than 1. And you can see that it kind of, sort of, it's hitting the actual signal function at a couple of different places every time, but it's not really that good of an approximation. If I increase that to n equals 2, you can see that that next term, 4 over 3 pi times sine of 3 pi x over 2, well, that puts an extra wiggle in, right? 3 pi over 2 is going to have 3 times as many goes around, and you get that up, down, up. And it's just enough to stay in the vicinity of that signal a little bit longer. When we put in the next term, it gives us just a little bit more, and a little bit more, and a little bit more. And as we continue, it gets better and better and better. It's never perfect, but it continues getting better. Although right at the point where the function changes, it's always a little bit messy, right? You have this pretty smooth signal, and then you have this part that spikes up, and then it spikes down, and you have this pretty smooth signal, and then it spikes down, and then it spikes up. For anyone who has ever done any work in signal processing, you should recognize that as the biggest bane in the existence of electrical engineering. The fact that our pulse square wave generators do this, because this is how square waves work. It's really hard to figure out how to get an automatic switching signal to give you a nice square wave. So instead, we get a bunch of nice sine waves, and we try to compress them down, and for the most part it works, and then all of a sudden it does something a little bit messy that's not quite as nice. So that's all a little bit above and beyond. Right? In general, finding that closed form of the summation is not usually easy, so we don't usually worry about it. But what I do want to point out is that I've gone here up to n equals 20, but if I'd stopped a good bit earlier, right, you don't really see that much of an improvement. In this case, after n equals 10, right, from n equals 10 to n equals 20. Yes, it gets better, but it doesn't get a lot better. And for a lot of applications, n equals 5 is really good enough. So if you weren't able to get a closed form for the general coefficient and type it in using a summation, you can still get a lot of valuable information out of it. And one of the interesting things that you might see if you take a course in Fourier analysis and signal processing at some point in the future, it is an interesting question of how big of an n do you need in order to get a good enough version of what you want with less data. All right, so that's beyond the scope of this course, but something that's worth considering as something that might be interesting. Let's wrap up with a problem for you to solve. F of x equals x for x between -1 and +1. Compared to the one that we just finished, the first thing you should notice here is that I've given it to you with that symmetric interval about the origin, so you don't have to worry about whether you need an even or an odd extension, although thinking about whether the function you have is even or odd in the first place is worth a little bit of time. I would like you to find a Fourier series to represent this function. If you can give me a closed form, that's fantastic. If you get a little bit stuck trying to find a closed form, if you can find just the first 5 terms, that's pretty good in and of itself. And then graph the function along with those first couple of terms and see what happens. Take a few minutes, see what you can do with that, and I'll see you in the next video.